webinar by Professor Dimitri. So we'll formally start of the webinar, and before starting, I would appreciate all the participants who have connected with us from different countries of OIC and from Pakistan as well. We have some physical participation at ComStech as well. We have around 20 plus people from Pinstech and Nilop and NCP at ComStech. Few of our participants have connected from Nilop College as well, and other participants have been connected with us virtually. So before we officially start, I'll just introduce one of our flagship programs about the ComStech Technology Innovation Portal. This is a flagship project of ComStech under the guidance of His Excellency Professor Iqbal Chaudhary. This has been formally launched. A proper portal website have been made, and I would request my colleague, Mr. Hasib, he will brief the audience about the aims and functionalities of the ComStech Technology and Innovation Portal. Over to you, Hasib.
Thank you, Haris. To begin with, like Haris said, ComStech has initiated its new project in the form of ComStech Technology and Innovation Portal. So before I go over the functionalities of the portal, I'll just brief you about what it is about and what do we aim to achieve by it. Basically, it is a portal that will provide a platform to help showcase emerging and existing technologies from across the OIC member countries. We have made it a very user-friendly portal that would connect the users with the relevant technology. We hope that it may assist in connecting ideas and prototypes to potential investors, and while aiding in industry and academia collaboration. If you look at the portal, this is our homepage. Over here, we have the search bar. If we talk about the areas of interest that we are inviting different products and services to be exhibited in are these. Basically, this portal provides option for two types of users. The first one is a user that basically is looking for technologies, whether they're looking for products, whether they're looking for services. We have an option here that lets you search for a specific product or search for a specific company. If I show you the option here which says browse products, here we have all the products that are being listed in the portal. This portal is just being launched, so it's open for all registrations now. When we are looking for different products, we have different filters that may help us to identify the products of interest. For example, we can look for a product in a specific area, for example, biosciences or energy. We can look for a product from a specific location, such as a country, or we can look for products at specific levels, whether it's a prototype or a commercial. For example, these are three products being listed from ICCBS. If we go into view details, we can see further details of the products, what their details are. We have different images. So basically, it provides a platform for different users to come and exhibit their products, their services from throughout the OIC. That will be a portal which will aim to bring forward the technology and innovations from throughout the OIC. The second is if you want to showcase your own product onto this platform, you basically have an option here which says join now. It's a very simple sign up procedure, basically using just your email ID. Once you sign up from here, you get a verification code on the email mentioned here. You add in the verification code and you're registered. After registering, it takes up to 24 to 48 hours for us to authorize your registration, and then you are free to post your products, your services onto this portal. Is just another look of our homepage. Our search bar is here. Here you can see all the latest products that are being added into the portal. So we invite all those in audience to visit our portal, to sign up, to register their products and services onto the portal, pass down this information, this link into your institutions, into your organizations, and through that we can populate this portal. If you have any issues regarding the portal while signing up or any queries that may come arise, you can contact us on either of these email addresses and we'll get back to you. The link of the portal is also now available for access on our ComStech website. Thank you.
Technology and Innovation Portal. Now I would request Professor Dr. Hamid Salim. He would like to introduce about the ComStech Basic Sciences program. Dr. Hamid Salim.
So, thank you, Mr. Harris and Hasib. First of all, I formally thank the speaker, Professor Dr. Dimitri Batani, for accepting our invitation to give this lecture. So we are very grateful to you. And now I would like to introduce the ComStech Basic Sciences program. This is the first activity under this program. And this program has been started to promote basic sciences, mathematics, physics, chemistry, and biology, and interdisciplinary areas in OIC countries. And generally, we would also like to interact with the advanced nations, advanced countries for the promotion of basic science subjects, because we believe that these science subjects laid down the basis for all the present sophisticated technologies. And this is the base for the present age of science and technology. So this is necessary for the intellectual growth of societies as well. And these subjects, we believe, and I think history tells us that they emerged from philosophical questions about the existence and dynamics of the universe. Then human needs promoted these subjects to invent technologies for the comfort of human beings and facilitating a high standard of living. And aim of this program is to make the fundamental concepts of these subjects very clear to the students of college and university. This is very important. And then to establish links between the scientists of OIC countries who are working in the fields of basic sciences. And this is a pleasure to say that Coordinator General of ComStech, Professor Dr. Iqbal Chaudhary, is very keen to promote this program. And he is a well-known chemist and highly cited scientist. And despite of being a chemist, he understands the importance of mathematical sciences. And I am happy that he has given this responsibility to me. And I am grateful to the young people of ComStech persons, Mr. Harris and Mr. Hasib. And especially Mr. Harris has been working closely with me. And I hope in future, we will introduce different programs. I briefly say that our main programs will be around the following three areas. First is that series of lectures will be arranged on topics of basic sciences, these areas, mathematics, physics, chemistry, biology, and interdisciplinary areas, to make fundamental concepts of these subjects clear to college and university students. And then we will arrange lectures on research topics, and those topics in which some active research groups are working in OIC countries. And third is that we shall request the scientists of advanced nations time to time to give lectures on these fundamental areas of research interests. So at the end, I am very grateful to all the people who are present here and who are joined this lecture through internet. And that's all. At the end, I again express my gratitude to all of you. Thank you.
Thank you, Professor Hamid, for giving us the introductory remarks regarding the Comstech Basic Sciences program. Now I would request Coordinator General Comstech, His Excellency Professor Dr. Iqbal Chaudhry, for his welcome address.
Good morning and good afternoon. Assalamu alaikum wa rahmatullahi wa barakatuh. Professor Dr. Dimitri Patani, Honorable Speaker of the first historical event in the history of Comstech, that we are starting a program which is very close to my heart. Being a practicing chemist, I fully understand and appreciate that basic sciences are the foundation of all major advances in science, technology, and innovation. Unfortunately, over the years, lots of fancy disciplines have emerged. And as a result, you would find scientists or pseudoscientists who do different things, but they have very superficial understanding of the basic concepts. And as I was exposed to this wonderful personality of Professor Dr. Hamid Salim, a scholar par excellence, he has this great capacity to convince people, and it took him only a few minutes to convince me that we should start a similar program as we have in UNESCO, but in a very different contour, that we would only be focusing on basic sciences and that we would be conducting activities all around the Muslim world, which is 57 countries. And these 57 countries, of course, they are least developed countries with lots of gaps and voids in education, technology, and different fields. But we felt very strongly that if we can emphasize on developing conceptual foundation of people, of students in these basic subjects, we give them the best gift, because then they will be able to build upon and can move forward into many other disciplines. So it's completely and honestly an extremely important program for which I am absolutely grateful to Professor Dr. Hamid Salim and his wonderful team for initiating it. I'm also grateful to wonderful speaker of today, and I assume the responsibility of introducing Professor Patani today. He has been working as a full professor at the University of Bordeaux, France. I visited Bordeaux, and Bordeaux is famous because of many reasons. Some of them cannot be mentioned on this forum, but certainly a beautiful town, a beautiful city of France. This is certainly an extremely important center for knowledge, as well as we keep sending many of our scholars to University of Bordeaux for various different kinds of trainings in the field of nuclear magnetic resonance spectroscopy, structural biology, and others. Professor Batani is working in Center for Laser Intense Applications since 2011. He has performed seminal work in several fields related to physics of laser produced plasmas, high energy density physics, laser driven sources of radiation and particles, and development of plasma diagnostic and physics of inertial confinement fusion. He has lots of publications, several hundred publications to his credit, 600 and above, which is certainly represent his extremely productive career, and H index of 47, and his work has been cited over 8,000 times. I'm sure that number is increasing, and by the end, he will finish his presentation. We will have a couple of more hundred citations to his credit. He's a member of the European Academy of Sciences and has been awarded the Fredel Volterra Prize 2017, jointly by Italian Physical Society and the French Physical Society, for this outstanding contribution in the study of laser plasma interaction related to inertial confinement fusion. He has several honors and awards and has served at many teaching and research positions. We are very fortunate to have a person of his stature inaugurating the first event of this ComStech Basic Science program. And as we foresee, we would be inviting him to different countries of the Muslim world. Many of them are Francophone, and if he can speak French, then certainly this is something which would add lots of value in it, because as I understand that he's an Italian. I may be wrong, but we are absolutely honored to have Professor Battani with us for this presentation. And we feel that's going to be a full forum because we already have 41 people joined online from different countries of the world, and we already have several classrooms filled with people in different institutions of Pakistan. Thank you very much, Professor Battani. Over to you, sir.
Thank you very much for your very kind and very nice introduction. So, as I said, it is a pleasure for me to be here today. I would like to thank all the organizers of this event, Professor Ahmad, Akram, and of course, Professor Choudhary, and my friend, Professor Salim, for having this opportunity. Several years ago, I took part in the Nyatagali summer school, and I remember really with pleasure my trip to Pakistan. So maybe I hope that I will be able to come in person soon. So I see that this is really an international event. I thought it was more related to Pakistan, but I see that there are many participants from Azerbaijan and other countries. So it is even a bigger pleasure to share this event with you. So I will try to share my screen and to start my presentation. So let's see, because so I have double screen. Let me see. Okay, let's try again. Sorry. So, do you see my screen, my presentation?
Yes, we can see your presentation. Yeah.
Okay, very good. So, my talk will be about an introduction and update on inertial confinement fusion. As you have listened from Professor Choudhary, I'm Italian. I spent biggest part of my research career in Italy. And then 11 years ago, I moved to France because I became responsible of a project which was called Petal Plus, which was really a project to realize the plasma diagnostics for the laser megajoule. I will speak about the laser megajoule later. So let's start with some very short historical introduction. The trip towards nuclear fusion for the production of energy started about 8 years ago. This is related to names like Sakharov in the Soviet Union and Teller in the United States. Well, you may notice that indeed these are the same person who collaborated to the construction of the atomic weapons in Russia and in the United States. And basically, after realizing the fusion, the hydrogen atomic weapons, they understood that fusion could also be useful to produce energy for mankind. Actually, at that time, they were very optimistic about the realization of possible fusion reactors. They said in 20 years, we will have fusion energy for mankind. And in reality, despite many progress, the research on nuclear fusion has provided many disillusions, And the path toward the realization of fusion reactors have proven to be much more difficult than what Sakharov, Teller, and other people thought at that time. So 60 years ago, the laser was invented, and soon after, several persons thought that the laser could provide an alternative path to realizing nuclear fusion. This is called inertial fusion. And it is related to names like Bazov in the Soviet Union, who is one of the Nobel Prize for the inventor of the invention of the laser, and Nuckols, who is maybe less well known. He was again, let's say, a student of Teller, working at the Lawrence Livermore National Laboratory. And today, we are still facing difficulties, but we are very close to the demonstration of ignition, which is the scientific feasibility of fusion in the laboratory. And this will conclude the first part of this travel. And then, of course, we still have to show that we can get high gain from nuclear fusion, and we can realize fusion reactors. So I will start with some very recent news that probably many of you have seen. In summer of this year, the researchers at the Lawrence Livermore Laboratory in the United States, using the biggest laser in the world, which is called the National Ignition Facility, have got an exceptional result. They got 1.3 megajoule of fusion energy by focusing a laser of 1.9 megajoule on a thermonuclear fuel target. So if we define the gain as the energy which is provided by the nuclear fusion divided by the energy of the laser, we have a gain of 0.7. So we define ignition when we have gain equal 1. That is, the energy provided by the nuclear fusion reaction is the same of the energy of the driver. So as you see, we are, for the first time in history, very, very close to achieving ignition. I will come back later to this result. But now let's step back and let's start from the basics. So the basics is this one. We have, I hope that you can see my mouse when I move it on the presentation. We have deuterium, which is an isotope of hydrogen, as you know, and tritium, which is another isotope of hydrogen. And if we can bring them very close to each other, the nuclear force will force them to merge, to fusion, and we will get, as a result, an alpha particle that is a nucleus of a helium atom, and a neutron. So this is this reaction here. Deuterium plus tritium produces alpha particle plus a neutron plus 17.6 megaelectron volt of energy, which we found as kinetic energy of the alpha particle and the neutron. There are many other fusion reactions, deuterium, which can produce tritium and hydrogen, or can produce helium-3 and neutron. Deuterium, helium-3, which produce helium-4 and the proton, and many others. Well, what is very important is the so-called cross-section, which is measured in Barn, which is a surface unit. And the cross-section tells us the probability of getting a fusion reaction as a function of the kinetic energy of the incident particle. So in this graph, you can see the cross-section for various fusion reactions as a function of the energy of the deuteron. And you see that the deuterium-tritium fusion reaction has two important characteristics. First of all, its cross-section is much bigger, which means that you have a bigger probability of getting the fusion reaction, so you will get more fusion reaction. And also the maximum for this cross-section is at much lower energy as compared to other fusion reaction. That is that the deuterium-tritium reaction is basically the easiest fusion reaction to be obtained in the laboratory. Well, there are two conditions which is important to satisfy in order to realize thermonuclear controlled fusion. Well, first of all, we must accelerate the particles to very high velocity. We need high velocity because these are charged particles, so they repel each other due to the Coulomb electric field. And only if they have a very high initial velocity, they will be able to approach each other to a very short distance before the electric repulsion push them away again. So in order to have some non-negligible probability of fusion, we need a temperature of 5-10 keV, which of course, as you know, temperature is a measure of the statistical velocity in a medium. You see, if I go back to this cross-section, the maximum for the reaction is at about 100 keV. At 10 keV, we are just here, which means that we are about 3 orders of magnitude smaller than the reaction, than the maximum. But of course, you realizing a temperature of 100 keV in the laboratory is today impossible. And realizing a temperature of 10 keV is very difficult. This is why it has been very difficult until now to demonstrate ignition and nuclear fusion. There is a second condition which we need to satisfy, which is the so-called Lawson criterion. That is, not only the particle must have a very high velocity, which translates into a very high temperature, but we must be able, to keep the fuel together for a long time, so to have a sufficient number of fusion reactions. Of course, the number of fusion reactions is proportional to the number of particles and to the time over which we are able to keep the fuel together. So this is called Lawson criterion, and it states that the minimum product of the electron density, which is the same of ion density because this is a hydrogen plasma, times the confinement time must be at least 1.5 centimeter. So there are 3 ways of realizing, of satisfying this condition. Well, the first one is gravitational confinement. Nuclear fusion is the source of energy of the stars. All the energy which we are getting from the sun is because the sun is a very efficient nuclear fusion reactor, like all the stars. Actually, in the stars, it is very easy to get nuclear fusion because you get a very high compression. In the center of the stars, matter is compressed to very high density. So you have a lot of particles, and you have a very high temperature. So this means that the stars are very efficient and they can make fusion starting from hydrogen, starting from protons. On Earth, we are not able to reproduce the fusion reaction as it is in the star, because this is a very complex cycle. From proton, you go to deuterium, from deuterium and proton, you go to tritium and helium-3 and so on. So it is a multi-step process. On Earth, we are only able to make a simpler we hope that we will be able soon to make a simpler process like fusion of deuterium and tritium. And then, concerning deuterium-tritium fusion, we have 2 approaches. magnetic confinement, and inertial confinement. And basically, if I go back to Lawson criteria, again, with today's science and technology, we are not able to get high density and high confinement time at the same time. So the two approaches are just based on the idea of getting high confinement time and low density, or very high density and low confinement time. So in my talk today, I will speak about inertial confinement fusion. And here I will just show you what is the principle of inertial confinement fusion. This is the direct drive approach. I will show you later that there is also an indirect drive approach, which is actually what has been used at the National Ignition facility in the US. But this is simpler, so we start from this one. So the typical thermonuclear target used in this kind of experiment is a sphere, which in principle is made by 3 layers. You have some ablator, some plastic or glass or diamond. I mean, there are different kinds of ablator. There is the DT fuel, which is a DT ice. It is in a cryogenic state. And then in the middle, you have some DT gas. So how does it work? You have many laser beams, and you focus them onto this target. And the irradiation with the laser beam produces the vaporization, produces the removal matter from the ablator, produces the vaporization of the ablator, so it produces a plasma. This is indeed the process which is called as laser ablation, which is also used in many applications, such as laser machining, for instance. Now, this plasma which has been created expands very rapidly, because it's very hot, towards the surrounding vacuum. And then, as a consequence of conservation of momentum, that is the third law by Newton of action and reaction, in order to counteract this expansion, you get a compression wave which compress the material. And if you are able to do this process in a good way, you will compress the material and you will be able to heat it so that you start the nuclear fusion reaction. And indeed, as I said before, we must be able to reach at least 5 kiloelectron-volt of temperature. And in order to satisfy at the same time the Lawson criterion, we must compress the DT to at least 1,000 times. It means that we go from the initial density of solid DT ice, which is 0.5 gram per cubic centimeter, we go to 250 gram per cubic centimeter. Well, there is an important point which we must consider. The targets which have been used in experiment and which we think that we will use in the future have typical dimension like a radius of 2 millimeters, and they contain a mass of about 1 milligram of deuterium and tritium. Now, if you calculate the number of ions which is contained in 1 milligram of deuterium and tritium, you will see that it is about 2 times 10 to the 20. Now, if you want to heat all these particles to a temperature of the order of 10 keV, you will see that the total thermal energy in the fuel will be about 1 megajoule. Now, the biggest laser in the world is the National Ignition facility, and it can at most deliver 2 megajoule of light on the target. Unfortunately, most of this light is not coupled to the thermonuclear fuel. Most of this light just go, most of the energy just go to create the surface plasma, the expanding plasma. And indeed, as I will show you later, only about 5 to 10% of the laser energy can be coupled to the thermonuclear fuel. So this means that it is impossible with present-day laser technology to take 2 10 to the 20 ions and heat them to 10 keV. So it means that volume ignition is not achievable. So we use a different approach, which is called hotspot ignition. So when at the point of maximum compression of the target, which is called stagnation, the fuel is made by a thick, dense shell and by a less dense central spot. This comes from the compression of the shell, and this comes from the compression of the gas, which was initially inside the sphere. We try to work so to heat the hot spot to a very high temperature. And this will generate alpha particle, which will deposit the energy in a thin layer of the fuel, because their propagation is very short, because this fuel around the spot is very dense. And we will create a nuclear bond wave starting from the hot spot. Now, this is how it works. In the hot spot, we can have maybe a low density, but we can get 5 or 10 keV temperature. So here we will have a nuclear fusion reaction. We will generate alpha particle, and this alpha particle will propagate into the fuel, and they will propagate in a very thin layer of the fuel, because their penetration range in the very dense material is very short. So this part of the fuel will be heated by the energy deposited by the alpha particle. So in this part of the fuel, we will also reach the condition for starting the nuclear fusion reaction. So this means that more alpha particles will be created. They will again propagate, and the process goes on. So we create what is called the propagation nuclear bond wave. This is also called as a self-heating regime, because actually it is dominated by the energy deposition from the alpha particle, which are initially generated from the hot spot. So how it is possible to create this hot spot? Well, basically, the temperature in the hot spot comes from the conversion of the kinetic energy of the imploding shell. So, as we said, laser ablation produces an expand high velocity. This produces a compression. They accelerate the shell towards inside, producing an implosion. So the shell gains kinetic energy, and of course the kinetic energy scales with the square of the velocity. So in order to, and then at the end of the implosion, the kinetic energy of the shell is converted into thermal energy of the hotspot. So in order for the hotspot approach to work, we need high implosion velocity. So, as I said, the hotspot is formed by the compression of the DT gas initially contained within the shell. And as the pressure increases, as the implosion goes on, the pressure inside the gas increases, and this pressure increase slows down the imploding shell. When the pressure of the gas equals the external pressure from the shell stops, and this is indeed the stagnation. And as I said before, at the stagnation, we want a density of about 250, 500, 1000 grams per cubic centimeter, and we want a temperature of 10 keV in the hot spot. Of course, this is also called an isobaric approach, because the pressure, you see that basically stagnation is created by the quality of the pressure of the shell and the hot spot. So it means that at the stagnation point, we will have an isobaric fuel assembly. In the hotspot, we will have low density and high temperature. In the fuel, we will have a very high density and lower temperature. And the pressure will be the same everywhere. So basically, the equality of the pressure implies, for instance, that in the shell you can have 1000 grams per cubic centimeter at the temperature of 1 kV, and in the hotspot you will get 100 grams per cubic centimeter at the temperature of 10 kV. And now, if the hotspot radius is 40 micron, then you can get a mass of 10 to the minus 5, 10 to the minus 6 grams, and the hotspot energy will be about 30 kilojoules. Sorry, yeah, I have to show this one. Actually, this view graph is misplaced. So this is the ideal situation. In the reality, is a bit more complex. This is a result from a hydrodynamic simulation of an if target imploded with 1 megajoule laser energy. And you see that the temperature profile and the density profile are not rectangular shape, but still you can see that there is a dense shell at very high density and lower temperature, and there is a hotspot at very high temperature and lower density. And you see, for instance, if you can calculate the pressure in the hotspot, which is okay, the same as the pressure in the dense shell, you can see that the pressure in this condition is about 600 gigabar, billion atmospheres. So this is an incredible pressure. And indeed, if you just make some simple calculation, you can see that the ablation pressure which is provided by the laser can only be of the order of 50 megabar. The pressure stagnation is of the order of 500 gigabar, which means that we need an amplification of pressure of the order of 10,000. And actually, this is provided by the spherical geometry. Because of the spherical geometry, during the implosion, the pressure increases. So actually, the spherical geometry is something which is essential. There are ideas using cylindrical geometry, but of course, in a cylinder, the compression is smaller, so the pressure amplification is smaller. So it means that making nuclear fusion becomes even more difficult. Okay, so let's go over. As I said, the hotspot is heated by the conversion of the kinetic energy of the imploding shell. And basically, the conversion efficiency from the laser energy to the shell kinetic energy is very low. It is about 5 or maybe at most 10%. So if you start with 1 megajoule, you will get maybe 100 kilojoule or less in the kinetic energy of the shell. And then this kinetic energy of the shell at stagnation is converted roughly into temperature of the hotspot, and roughly 50% in temperature of the hotspot, and roughly 50% in the compression of the fuel. Well, this is again the same view graph, but this has been I got it from Riccardo Betti at the University of Rochester, who in University of Rochester is the home of the Omega laser facility, which is another big laser. And again, you see the expanding ablated plasma. You see the DTIs, which is imploding with certain velocity. the kinetic energy is 1/2 the mass of the fuel, which is the mass that you are not going to ablate during the implosion, times the implosion velocity square. And this is about 5 to 10% of the laser energy. And that compression and stagnation, it is converted roughly half in compression and heating of the hotspot, and roughly half in compression of the dense shell. Well, some order of magnitude. If we have a radius of 2 millimeters, and we want to get an implosion velocity of 400 micron per nanosecond, we will see in a second why. This is the implosion velocity during the implosion phase, but in the beginning, you have to begin to accelerate the shell, and then at the end of the process, the shell slows down. So the average velocity will be roughly half of this value. And now the implosion time, 2 millimeters divided by 200 micron per nanosecond, will be about 10 nanoseconds, which is indeed more or less the duration of the laser pulse at the National Ignition Facility. If the laser energy is 1.5 megajoule, you can calculate the surface of the target, and you get the intensity on target, which is about 3 times 10 to the 14 watt per square centimeter. Actually, this is not a very high intensity. Today, we have laser systems which are able to provide 10 to the 18, 10 to the 19, 10 to the 20 watt per square centimeter. The point is that we want to use an intensity which is not too high, because in this case, we control much better the interaction of the laser with the plasma. If we go too high in intensity, the interaction becomes strongly nonlinear and basically becomes almost uncontrollable. You see, if we have a mass of 1 milligram, about 1 milligram, and the velocity of 400 kilometers per second, the kinetic energy in the shell will be about 60 kilojoule, which is indeed in agreement with the estimation which I made here of the hotspot energy of 30 kilojoule, which we need in the hotspot. Well, now comes the problem. How can you get such a big velocity? Well, in order to get such a big velocity, you have to use a small mass. Because it is, of course, much easier to accelerate a small mass than a big mass. You could say that indeed you could get the same kinetic energy by getting a smaller velocity and getting a bigger mass. But I mean, the dependence on mass is just linear, and the dependence on velocity is quadratic. So it is much easier to get 60 kilojoule by using a small mass and a high velocity. But using a small mass that is a very thin shell means that these thin shells are very sensitive to deformation and can break during the implosion. And if they break, of course, the process stops. Actually, how it breaks is the result of a hydrodynamic instability, which is called the Rayleigh-Taylor instability. I think that most of you are probably already familiar with this instability. You know that if you get a glass of water and you reverse it, the water will fall down. I mean, everybody has experienced this many times in life. But why the water falls down? Actually, it is not because of the force of gravity, because the pressure of the air is much stronger than the force of gravity on the volume of water which is contained in the glass. Actually, the pressure of air is sufficient to sustain a column of water of several meters. indeed, if you reverse your glass, but you put a foil of paper, the water will not fall down. And it is not because of the foil of paper, because this is making no force, basically. The water falls down because of the development of Rayleigh-Taylor instability. So the situation in which you have water up and air down is unstable according to the Rayleigh-Taylor instability, which means that if you consider that the surface of separation between water and air will get small perturbation, the perturbation will grow in time. It is an unstable behavior. And they will grow and grow until they will reach a size which is comparable with the dimension of the glass, which means that indeed the water will fall down. Sorry. And in laser fusion, you have the same kind of laser of hydrodynamic instability. This is more or less the situation. Right? What are you trying to do in laser fusion? You have the expanding plasma, which is a light fluid, and you want to compress the shell, which is a dense fluid. It is exactly like the water. I mean, you have air, which is a light fluid, and you try to keep in place water, which is a dense fluid. And now, because of the instability, it means that you will get perturbation. The perturbation will develop in time. And you can see, I mean, the images are really very beautiful, but the reality is that you will break the shell. And of course, this instability develop even starting from noise. But if you have non-uniformities in the target surface, in the target density, or if you have non-uniformities in the laser irradiation, then this will act as the seed of Rayleigh-Taylor instability. And this will, and in this case, the Rayleigh-Taylor instability will develop much faster. So it means that a crucial point of laser fusion is to have perfect targets and to deposit the laser energy in the most possible uniform way. Well, there is a final difficulty in for inertial fusion. That is that in order to reach a very high density, you must be able to realize a gentle compression. Okay, of course, gentle is relative because we are speaking about pressure of 50 megabar, of several hundred gigabar at the end. But you must be as gentle as possible, which means that you must realize a quasi-adiabatic compression. In other words, it means that during compression, you want to heat the material as the fuel as a result of compression. You don't want to heat more than this, because if you heat it too much, it will be much more difficult to compress it. You know that it is more difficult to compress a hot gas than a cold gas. So how can you make this gentle compression? Well, you need what is called a laser shaping, laser temporal shaping. You have a laser intensity which is small at the beginning, and then it follows the implosion. As the pressure of the target increases, the laser intensity also increases. So we can introduce a parameter which is called the adiabat parameter alpha, which is the ratio of the pressure, which is the ratio of the pressure which is achieved in the compression to the pressure which would correspond to a perfect adiabatic compression. So in a way, if alpha is equal 1, we have made a perfect adiabatic compression. If alpha is equal 2, at the end of the compression, the pressure will be 2 times the pressure of the perfect adiabatic compression. So for inertial confinement fusion, we want to realize alpha as small as possible. Now, let's come to the so-called indirect drive. Until now, I've spoken about the direct drive approach. The laser are focused on the target. They produce the vaporization, they produce the implosion, which goes on until stagnation. Sorry, sometimes it's difficult to control. But there is another approach, which has indeed been used at the National Ignition Facility, which is called indirect drive. How does it work? Well, sorry again. You have a cavity, which is called all round with the German word, and the laser beams are focused on the internal holes of the cavity. So this is IZ, it can be gold, it can be even uranium. And the laser beam produces a hot plasma on the surface of the internal surface of the round. This hot plasma emits X-rays. You know by the law of thermodynamics that the wavelength of emission from a body is inversely proportional to the temperature. And if you have a temperature of the order of plasma temperature in the order of a kilo electron volt, the emission from the plasma goes into the X-ray region of the electromagnetic spectrum. And it is these X-rays which are absorbed by the capsule and produce the vaporization and the implosion. So why we do this scheme, which of course is much more complicated than direct drive? Well, not only is much more complicated, but in this scheme, we lose a lot of energy because the laser energy is not directly used to compress the target, but it is used to produce X-rays. And in this conversion of laser light to X-rays, actually we can lose as much as 50% of the energy. So why we do this? Actually, the important point is that due to the confinement in the cavity, the X-rays which are generated very quickly becomes very similar to a black body radiation in the X-ray range. And of course, you remember from the law of thermodynamics that the black body radiation has some very nice properties, like that it is uniform and isotropic. So now it means that if you are able to use this X-ray to drive the implosion, you will get a much better implosion, much more uniform. So the idea which has driven the experiment on NIF was that we are not able to get a sufficient uniformity of irradiation when we use the laser directly. And so we must go through this step in order to improve uniformity and to remove the seed for the development of the Rayleigh-Taylor instability. So now let's come to some, again, to some recent history. NIF is operational since 2000 something, and in 2009, they started what was called the National Ignition Campaign. So in 3 years, they were planning not only to demonstrate ignition, but to demonstrate a gain of 20. So the aim of the National Ignition Campaign was to produce about 30 megajoule of laser energy, of fusion energy, starting with a laser providing 1.5 megajoule. So gain of 1 implies, of course, the energy provided by the fusion reaction is proportional to the number of reaction, and then it is proportional to the number of neutrons, because we have 1 neutron per fusion reaction. So gain equal 1, that is fusion energy equal 1.5 megajoule, implies that the number of neutrons should be about 5 × 10⁻17. But in reality, in the national ignition campaign that only got 10 to the 15 neutrons. And this was very disappointing for NIF. It was very disappointing for all the community, because at that time, everybody was really confident that they were going to succeed. Well, actually, there were many problems which brought to this failure. One problem is, of course, the fact that this experiment, this implosion, were designed using very complicated simulation code. And this simulation code need to use equation of state data, that is how the materials behave at very high pressure, how we can get compression when we apply the pressure. We need they use opacities, that is the data on how the materials emit X-rays and absorb X-rays, and so on. And these data were incomplete. There was an underestimation of the impact of parametric instability, like stimulated Raman scattering, stimulated Brillouin scattering, which can reflect a large part of the laser light. Again, as I said before, we want to use an intensity which is not too big, because otherwise this parametric instability completely dominates the laser plasma interaction. But unfortunately, even in the case of NIF, the parametric instability were stronger than it was predicted. There were problems on how you keep the pellet inside the round. This must be kept somewhere, and they used a very thin membrane. And this thin membrane actually, unfortunately, acted as a seed of Rayleigh-Taylor instability. And indeed, the main problem related to the failure of the national ignition campaign was the underestimation of the impact of Rayleigh-Taylor instability. And if we can drive a conclusion after this failure, I would say that it clearly showed that the goal of achieving ignition and gain is still a scientific challenge and not only a technological challenge. And of course, when you have to build a bridge, a nuclear power plant, a submarine, you can make an estimation of how much time you need. But when you have a scientific challenge, this is somewhat unpredictable, because you can always find a difficulty that you didn't expect at the beginning. And I would say that this is also true for magnetic confinement fusion at the moment. Well, after the end of the national ignition campaign, they continued the experiment. They were changing a bit more. I mean, during the initial campaign, they make many shots. They were trying to improve, but in a way, they were sticking to the initial design. And after this, they had the possibility to change a bit more. And you see, in 2013, they got much better result. And the much better result is not only because they got many more neutrons, they got a bigger yield for nuclear fusion. The much better result is related to this red bar as compared to the blue bar. So the blue bar is related to the yield, that is the number of nuclear fusion reaction that you get because you compress the target. So, I mean, you bring the target to some temperature and some density, and using this parameter, you calculate the number of fusion reaction. The red bar is related to the contribution which is coming from the alpha part, from the generated alpha particle, which deposit their energy heating the fuel. So you see, in the shots during the national ignition campaign, this contribution from alpha particle was negligible. And then here it was about 50%. So it means that really the process of self-heating from alpha particle is becoming important. And if you remember what I said at the beginning about the need of a thermonuclear Born wave, you see that This is really the good news. It means that you are beginning to approach the regime of self-heating. In 2014, they improved the result again. So how this was possible? Actually, it was possible for several reasons, but mainly because they changed the shape of the laser pulse. During the National Ignition campaign, they used the so-called low-foot pulse shape, which starts very gently and then increases the intensity. In the better result, which they got later, they were using a high-foot laser pulse, which means they start to a bigger intensity. Well, from what I said before, you could say that this is the low foot is the good laser pulse, and the high foot is not good, because you are focusing a laser with a too big intensity on the target, so you are hitting the target too much, so you are producing a compression with the worse adiabat. And this is true. So why they got better result? Actually, they got better result because the high foot laser shape could minimize the impact of Rayleigh-Taylor instability. So if you look at the growth rate of Rayleigh-Taylor instability, in the case of water and air, gamma, the growth rate of the instability, is simply given by the square root of A kg. A is the Atwood number, which is related to the densities of the two materials. K is the wave vector of the perturbation, and G is the accelerating field. In the case of laser plasma, this is a bit more complicated, and actually it is a bit better because there are some mechanisms which are partially stabilizing the Rayleigh-Taylor instability. These mechanisms are due to the presence of a gradient of plasma. You know, in water and air, you have a sharp interface. Here, you have a plasma density which is gradually decreasing, which means that you have less space for the instability to grow. And you have the ablation of the plasma. So you have some plasma where the instability begins to grow, and this is brought away by the ablation. And you see, if you have a bigger intensity, it means that you have a bigger ablation velocity and you create a longer plasma. And these two stabilize better the Rayleigh-Taylor instability. So you see, the low foot implosion, in the low foot implosion, they got implosion with alpha equal 1. In the high foot implosion, the adiabat was much worse. It was 2.8. But because of this stabilizing mechanism, the impact of Rayleigh-Taylor, you see this simulation in the two cases, was much smaller. Here you see that the shell is breaking, basically, and here you see that the shell is deformed, but is not breaking. So after 2014, they continued the campaign. They got improvement, changing the shape, changing the type of ablator, changing the many things. And then last year, they got 150 kilojoule of fusion energy. And this year, I come back to my initial view graph, they got 1.3 megajoule of fusion energy. If we compare this graph, with what happened later, this is what they got in 2020, the original graph. This is what they got now, and this is the original graph. So you see the huge increase which has been done. So let's look a bit more at this laser system which have been, which are realized. So this is a scheme of the National Ignition Facility. You have the so-called laser bay, and you have about 200 laser beam, which are transported to the interaction chamber. inserted in the interaction chamber and focused on the target. The laser megajoule in France is basically the twin of the NIF. There are small differences. And actually the two projects started together about 20 years ago. But of course, because the economical power of the United States is much bigger than the economical power of France, the project of NIF proceeded much faster, and NIF has been working now for 10 years and more, and laser megajoule is about to be completed now. There is something which is very important. If you look at the schema of how the laser beam arrives to the interaction chamber, you see that they are not uniform. They come into two poles, up and down. And basically, these are exactly corresponding to the entrance hole of the all-round. So these, the distribution of the laser beam is not uniform on the arrival of the target chamber. These are some pictures which have been taken during the installation of the National Ignition facility. This is the building, and by using Photoshop, they put 3 fields of American football on the top of the roof just to see what is the dimension. This is the interaction chamber of NIF, which is basically identical to the interaction chamber of the laser megajoule in France. The diameter of this chamber is 10 meters. And we need such a big chamber because if we are able to do ignition and gain, the energy released by the fusion will be so high that we need the big chamber in order to reduce the energy load per unit surface on the wall. This is the NIF chamber as it is now, with the laser beam which are arriving to the chamber and with other openings for diagnostics and for everything else. This is just for the science fiction movie lovers. Actually, a part of the movie Star Trek has just been turned around the chamber of the National Ignition facility. And now we'll go to the laser megajoule. Laser megajoule, as I said, is practically identical to the NIF. The main difference is that the interaction chamber is in the center and you have half of the laser beam on one side and half of the laser beam on the other side. You see the building is 300 meters long, which means that it is about the size of the Eiffel Tower. And it is 40 meters high. So I compared with some well-known monument in Pakistan, which is, again, 43 meter high. So it can really gives you an idea of the dimension of this laser. And you have 176 beams, which will be at the end of the construction of megajoule, deliver about 2 megajoule of energy on the target. So we have very good news. We are very close to ignition. But, I think that demonstration of ignition is an enormous scientific achievement. However, NIF is based on indirect drive. And in my opinion, indirect drive is not compatible with the requirements for future fusion reactor because you have complicated targets. You have the all-round and all the laser beam must be focused through these two holes. So now you can imagine that NIF can make today 2 shots per day, but a fusion reactor will need to work at 1 Hertz repetition frequency or even more. So you can imagine that putting this target at 1 Hertz, aligning them and so on, is going to be practically impossible. Also, these are massive targets because you have the all-round, which is maybe 2 centimeters times 1 centimeter. This is the actual size of an all-round. So it means that at each shot, you have a lot of IC material which is injected into the chamber. So if you work at 1 Hertz and you have a realm of gold, after 1 day, your chamber wall will be fully covered with a layer of gold. And above all, indirect drive is intrinsically low gain because to the energy which we lose in the step of X-ray conversion. And there is a final problem that indirect drive poses political problem because in a way, this process on a micro scale is similar to what happens in, there are similitudes, let's say, to what happens in a hydrogen bomb. So indirect drive is considered to be proliferating. So for all these reasons, I think that we need to go to direct drive. But how can we mitigate Rayleigh-Taylor instability in direct drive? Well, there are ideas. And one recent idea, which I like very much, is the so-called shock ignition approach to inertial confinement fusion. So this is the laser pulse used in the classical ignition. As I said, small at the beginning, and then it increases. And this is again, and this is the laser pulse which you use in shock ignition. So you have the same, but you start with much lower intensity. And then at the end, you have a very big, very high intensity ignition spike. So why this change and why it minimizes Rayleigh-Taylor instability? Well, look at this one. You have a very much smaller energy, which means that you will not be able to accelerate the shell to a very high implosion velocity. You will not be able to reach 400 kilometers per second. Maybe you will be able to reach half of this value, 200 kilometers per second. So it means that you will be able to compress the fuel, but you will not have kinetic energy sufficient to produce a required temperature in the hotspot. But then, at the end of the stagnation, we launch the very high intensity spike. And this creates a very strong spherical shock wave, which converge towards the center. It reaches the gas inside the target, and it provides the additional energy needed to reach the temperature for fusion. So the big advantage is now that basically what we are doing, we are separating the phase of compression and the phase of ignition. In the classical ignition, they are together. I mean, the same laser pulse is creating the condition for starting the nuclear fusion reaction. Here we make the compression, and the final laser spikes create the condition for the fusion reaction. The big advantage is that since we do not need a very high velocity, we can use more mass. We can use a thicker shell, and the thicker shell is much less sensitive to the effect of the Rayleigh-Taylor instability. It will not break during the implosion. These are just some kind of simulation which show that indeed, if you have a laser pulse like this, the Rayleigh-Taylor instability is very big. And if you have a laser pulse with the spike at the end, the laser-Taylor instability, it is much smaller. I'm just approaching the end of the seminar. I would like to say that there has been some preliminary experiments at the Omega Laser Facility in the United States, which show that the approach is promising. Okay, the Omega Laser Facility is not a megajoule laser. It is much smaller. It can provide the energy of about 60 kilojoule. But it is the only facility in the world today, which is the high energy facility in the world, which is dedicated to direct drive. So in experiment, they compared the neutron yield from using a normal laser shape and using a pulse, which is shock ignition-like. And okay, here, unfortunately, the color are reversed, but with the spike, they got a much better performance from the implosion. So shock ignition is very interesting, but there are very many unknowns. Basically, these are related to the fact that the final spike should have an intensity of 10 to the 16 watt per square centimeter. And this is exactly the range of intensity which we wanted to avoid because of the strong impact of non-linearities, of the strong impact of parametric instabilities. So we have to make experiment to study the impact of parametric instabilities in this regime. And also the parametric instability have two effects. One effect is to reflect a lot of laser light, but the second effect is the production of hot electrons. And these hot electrons in inertial confinement fusion have always been considered very dangerous because they can penetrate deeply into the targets. They can preheat it. It means they can increase the temperature and make the compression much more difficult. So actually, in inertial confinement fusion, in the classical approach, a very key question was always to avoid hot electrons. Now, in the shock ignition, we have high intensity in the spike, and we will have hot electrons. But actually, in this case, we don't know what will be the effect, because at the end of compression, the target is very dense. It means that what is called the areal density, the product of the density and the radius, the rho r, is very large. So it means that the hot electrons, if they are not too energetic, will not be able to penetrate. They will be stopped in the outer layer of the fuel. And in this case, not only they will not be able to preheat, but they can also have a positive effect. They can contribute to increase the shock pressure. Okay, this is just a view graph showing how it works, but I skip it because it's a bit, maybe we can come back later to this if you want. There has been an experiment at the Omega Laser facility which showed that probably they've been able to produce shocks, converging spherical shock of pressure up to 300 megabar, which is what we think is necessary for doing shock ignition. But okay, but this experiment is a bit controversial. But I mean, the scientific community is studying all the problems related to inertial confinement fusion, and in particular, my group in France is also focused on the physics of shock ignition. But there is another problem. The problem is that the machines which we have today, megajoule, NIF, and also the Shengguan 3 laser in China, which is a bit smaller, but it is still a very big laser, they are conceived for indirect drive. The laser beam do not arrive uniformly on the target. So now, if we want to make a shock ignition experiment in direct drive, we have to rearrange the laser beam. We need to depoint the laser beam which are arriving here on the top and on the bottom. We must depoint them so to arrive on the surface. The problem is that when you depoint the beam, it is not arriving normally, it is arriving at an angle. So the focus spot of the laser beam will be bigger, so the intensity will be smaller. So if you want the same intensity everywhere, now you have to reduce the energy of the beam which have not been depointed. So you end up with 1.5 megajoule of laser. You have a 1.5 megajoule of laser energy initial, initially, and after this operation of depointing and reducing the energy, it turns out that you can only use 500 kilojoule. But maybe 500 kilojoule will be enough to get ignition in the shock ignition direct drive approach. So we are working in order to try to get a demonstration in the future, demonstration experiment on NIF and megajoule. This approach is so-called the polar direct drive. You use a beams which are concentrated to the poles, and you depoint them to get a direct drive approach. So before getting to this demonstration experiment on LMJ, NIF, on Shenzhen 3, we have still to solve a lot of physics issue related to hydrodynamics, related to the control parametric instability, and so on. And luckily, this for solving this issue, in some cases, we do not need the very big laser. This can be done on smaller lasers, like the laser which are available in Europe, Gecko in Japan, Shenzhen 2 in China, Omega in the United States. So in conclusion, I think that today there is a lot of interesting physics which we can, which we want and we can study on big laser facility, but also on intermediate laser facility. And our goal is to demonstrate that using polar direct drive, we can make direct drive experiment on NIF and LMJ, in particular using the shock ignition approach. So I believe that this is an exciting field for research in physics and in engineering for young people at the beginning of their career. So another conclusion, we are entering a new era in fusion. We have big machines like NIF, LMJ, and other laser systems, and we have also big machines which are going to be built in magnetic confinement fusion. So I believe that we are really at the edge of demonstrating ignition in both magnetic fusion and inertial fusion. And we need to define a strategic way forward in order to get gain and to be able to have in the future fusion reaction. Of course, there are still some unanswered questions which are maybe unpredictable, but let's say, let's be a bit more optimistic. Thank you very much for your attention. I've been a bit longer than expected, but now if you want to ask any question, please.
Hello, Dimitri, can you hear me?
Yes, I can hear you very well.
Okay, so thank you very much. Very exciting and informative lecture. So we invite questions if people want to ask. What is the I can ask at the end. Only one question, Dimitri, very simple. That the ablation velocity must be smaller than ion acoustic speed, because after all, this is a plasma.
Sorry. Because I lost your word. The ablation velocity must be
smaller than ion acoustic speed.
Yes.
Because after all, it is a plasma.
Yes. Well, yes. I mean, the implosion velocity. Okay, I didn't go into the details of this one, but basically the implosion follows a rocket model. So in a way, it is a spherical geometry, but apart from this, it is very similar to a rocket. In a rocket, you have the gas which is expelled, and as a result, the rocket moves in the other direction. Here you have the plasma velocity, and you and you get the implosion of the shell. And actually the implosion of the shell accumulates in time because, I mean, it is like a rocket effect. So the ablation velocity can be small, but you can get to final high implosion velocity. I don't know if this is the answer to your question.
Okay, so I think many people are waiting for questions. Otherwise, I also want to ask one thing more, that the magnetic field generation, although it is not very important as far as fusion is required or implosion is required, because magnetic pressure is much smaller, beta is much small. But the point is that the vorticity, I think ablation, when ablation takes place, the speed generated or ablation velocity has vorticity inbuilt in it. Do you want to comment on it?
Yes, well, actually, I'm not a real expert on this. You are much more expert than me on this kind on this topic. Yes, yes, you are. But what I know is that the impact of magnetic field has been considered in the indirect drive approach, and it has been seen that indeed there are several effects from the magnetic field in the indirect drive approach because of this geometry, which is, let's say, cylindrical. In the direct drive, due to the spherical geometry, there are not magnetic field at the on a large scale. You can still have a magnetic field at the micron scale, as you said, but in general, it is thought that the impact of magnetic field is much less severe in direct drive as compared to indirect. And actually, there have been experiments using different kind of diagnostics, which have really shown the presence of the magnetic field in the all-round.
Thank you, Professor Dimitri. I'm Naseem. I have already met you in Pakistan some years back. I have one question. We are using a high density of carbon as a ablator material.
Yes.
If there is a instability generated in that for the case of adiabatic compression, if we need to compress the fuel in adiabatically, is there any instabilities are formed in high density carbon or foam?
Well, actually, you know, in the NIF experiment, they tried a different kind of ablator. They initially used plastic. They used plastic with some dopants. They tried to use glass, and finally they moved to diamond-like, this so-called high-density carbon. And it has proven to be a much better ablator. And basically, what they saw is that indeed with the high density carbon, they could reduce even more the impact of the hydrodynamic instabilities. Now, I'm not sure about the details of how this was possible. I'm sorry, but the result is that it was behaving better than other kind of ablators.
You have mentioned beryllium also for the ablator material. Which one is better for a beryllium or high density carbon?
Okay, sorry, yes. This beryllium was also something that they tried. At the moment, high density carbon has provided the best result. But I think that, I mean, there is not still a finite answer. The experiments are going on. In particular, they are going to have an experiment before the end of the year in which they want to repeat the result that they got in August. Well, there is also something interesting about this result because they were really trying to do their best, but they were not expecting 1.3 megajoule of laser energy. They were expecting maybe half of this value. So this shows two things. So it shows that indeed we are on the good slope. It means when the self-heating starts, it proceeds in a way by itself. You know, it's like when you try to, the self-heating process is something like when you try to light a fire. You do not want to light the whole wood. You start with the match, and then the process goes on by itself. So once the self-heating of a particle starts, we can get very quickly to ignition and to gain, because the process goes on by itself. So in other words, it is much more difficult to go from gain 0.01 to gain 1 than it is from gain 1 to gain 100. And now we are all we are waiting for the experiment which they will do before the end of the year. Of course, we hope that we will get the same result or even better, but in a way, because we are just at the beginning of this slope, any small fluctuation can bring us very different results, better or worse. So,
Thank you, sir.
I would like to say that if somebody wants to send me, I will make the presentation available for all the persons who have taken part in the presentation today. I mean, you of course have recorded the presentation, but I can send you the PDF file, which is maybe lighter. And if anybody wants to contact me for asking questions, even after today, just write an email to me. I will put my email in the PDF of the presentation, which I will send to Professor Salim for distribution.
So Dimitri, at the end again, I would like really from the core of my heart, I am very grateful to you. This was our first activity under ComStech Basic Sciences program. And I think Dr. Iqbal Chaudhary will be happy if we continue such programs in future as well. I am also very thankful to all the participants who are here. And we have actually invited very few who requested us to come here because of Corona. Otherwise, I think we can arrange much larger audience here. And from OIC countries, I think many people have joined and listened to your lecture from other countries. And at the end, I can only say thank you to all the friends. And Dimitri, I am grateful and happy to see you after I think many years, more than 5 years.
Yes.
So thank you very much.
Thanks to you. And it was a pleasure to give this talk. It was a pleasure to see you all again. And let's hope that we will be able to meet in person soon.
Sure. Thank you. Thank you.
Bye.